Chapter 12, Section 2, we're going to cover two of the trig standards, and that's to calculate values of the 6 trig functions, the 3 main functions and their inverse trig functions. And we need to know the identity cosine squared of x plus sine squared of x equals 1. So our objective today is to deal with trigonometric functions of acute angles. Now, a trigonometric ratio starts with a right triangle, and it involves one angle and two sides. So here's our right triangle. Here's the angle that we're dealing with, which I know it looks like a 0 with a line across. That's the Greek letter theta. Here's our right angle. From theta's point of view, this side is the side opposite this angle. And this side, the longest side, is the hypotenuse. That's always the one that the right angle points toward. And the name of this side that's left is adjacent. Now I know the hypotenuse is adjacent also, but it's got the name hypotenuse, so we're going to use this adjacent. Also, if we consider that this point here is a point x and y, that the adjacent side can also be named the side x on an x and y axis. The opposite side could be called y. And when we talk about unit circles tomorrow, you'll see that the hypotenuse we sometimes call the radius as well. So what we need to do is to learn those 6 trigonometric ratios. So with one angle and two sides, if we take the ratio that puts the opposite side over the hypotenuse, or which is y over the radius, that's called the sine function. If we start here at theta and look out, take the ratio of adjacent over hypotenuse, or in our other notation, x over r, that's called the cosine function. Next, if we again stand at theta and look out over the triangle, if we take the opposite side over the adjacent side, that ratio, or using our other notation, y over x, that's the tangent function. These are the 3 main trig functions, but there are 3 more which are inverses of that. So sine, and this is the abbreviation for cosecant, CSC. So cosecant is the reciprocal. If sine is the opposite over hypotenuse, cosecant is the hypotenuse over the opposite. So again, standing at our theta angle, we take the hypotenuse over the opposite, which is also r over y. That's the cosecant. The reciprocal of cosine is secant. And so if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. So again, standing at our circle, we take the hypotenuse over the adjacent, or r, the radius, over the x component, and that defines the secant. The last of the 6 trig ratios is the inverse or reciprocal of tangent, and that's cotangent. So if tangent is opposite over adjacent, cotangent is the reciprocal, adjacent over opposite. So standing here at theta again, looking out over the triangle, we take adjacent over opposite, or in our other notation, the x component over the y component. That's the cotangent ratio. Your first job is to memorize those 6. And so I have a few little memory devices for you that may help. For sine, cosine, and tangent, some students like the SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. This is one I learned in school. Oscar had a heap of apples. If you look at sine, cosine, and tangent at OH, Oscar had AH, a heap, OA of apples. This next one's not politically correct, but it works. They take the S from sine, SOHCAHTOA, which we already had the SOHCAHTOA. But to make words out of it, this is an old one that's been around since I was in high school. Some old hags can't always hide their old age. I know that's not politically correct, but if it helps you remember things, that's important. I had a contest one year, and here's what a student came up with that is more politically correct, and they were a person that was an equestrian type. So they said, we saddle our horses, which is sine opposite over hypotenuse, canter away happily, which is cosine adjacent over hypotenuse, towards other adventures, which would be the tangent opposite over adjacent. For the reciprocals, cosecant, secant, and cotangent, this is one that a student came up with in a contest. So for the reciprocals, Clausen helps our smart heads at calculating algebraic operations. So that's the cosecant is hypotenuse over opposite, the secant is hypotenuse over adjacent, and the cotangent is the adjacent over the opposite. Now, some other ones for the three reciprocals is you might want to think of it as CSC, which is the abbreviation for cosecant. At Christmas, Santa Claus says, ho, ho, ho. So that's hypotenuse over opposite. Secant is the funniest one. That's ha, ha, ha. So if you're playing the game Pin the Tail on the Donkey and you can't see what you're doing, that's quite a funny thing to watch. So that's ha, ha, ha. That's secant is the hypotenuse over the adjacent. Cotangent, I know, this is kind of a strange one, but calypso music, all the good old calypso songs had an AO somewhere in that. Somebody was singing AO, AO, you know, daylight coming, we want to go home. So cotangent is AO, adjacent over opposite. Whichever memory device works for you, as long as you can remember what they are, it's important that you memorize them and start memorizing them today. All right, let's move on to solving some problems with that. So example 1 says we have an acute angle theta. It's in standard position. So again, that means its positive x-axis is where its initial side is, and its terminal side goes through the point 4,5. Well, let's try to see a picture of what that is. So here's our positive x-axis, here's our positive y-axis. We have our angle theta, and it goes through the point 4,5. Now, of course, that means the x component is 4, the y component is 5. Now, once we found that, we want to find sine, cosine, tangent, cosecant, secant, and cotangent, all 6 ratios. We want to practice that. And to do that, we need to find the hypotenuse, because that's missing. So we've got a 4 and a 5 for 2 sides. Let's use the Pythagorean theorem, and let's take this radius, or hypotenuse squared. That's going to be the sum of the 2 sides squared, so 4 squared plus 5 squared. So the radius squared is 16 plus 25, or the radius squared is 41, which means that r, the hypotenuse, is the square root of 41. Now that we have that, we can come up with the solutions here. Sine, standing at this, is opposite over hypotenuse. So 5 over the square root of 41. Remember, we can't leave a radical in the denominator. So if you multiply both the numerator and denominator by the square root of 41, that gives you 5 square roots of 41 over 41. Cosine, remember, is adjacent over hypotenuse. So for the cosine, if we stand here at this angle, the adjacent side is 4, the hypotenuse is still the square root of 41. We still cannot leave a radical in the denominator, so multiply numerator and denominator by the square root of 41. That gives us our answer is the cosine is 4 square roots of 41 over 41. Tangents from here is opposites over adjacent. So that's 5 over 4. That works out nicely. Cosecant is the reciprocal of sine, and it's helpful to learn the reciprocals. So sine, well, let's stand here at theta again, and cosecant is going to be at Christmas, Santa Claus says ho, ho, ho. So that's hypotenuse over opposite, or the square root of 41 over 5. No radicals in the denominator, so we don't need to simplify that fraction anymore. Secant is the reciprocal of cosine, and secant, playing pin the tail on the donkey, that's the funniest one, so that's ha, ha, ha. So putting the hypotenuse, square root of 41, over the adjacent, which is 4, that's the square root of 41 over 4, and again does not need to be reduced. Cotangent is the reciprocal of tangent. That's that calypso AO thing. So standing here, we're going to go the adjacent over the opposite, which is 4 over 5, or 4/5. So that's finding all 6 trig ratios based on the clue we had that the angle in standard position, its terminal side, goes through the 0.45. We knew the x component, the x value had to be 4. The y component, the y value had to be 5. We used the Pythagorean theorem to find the hypotenuse. And then we used our 6 trig ratios that we've memorized to fill in the numbers in that spot. Alright, now that we've done a simple reminder of our trig functions from Algebra 1, we want to talk about what a trigonometric identity is. A trigonometric identity is an equation that involves trigonometric functions of an angle theta, and it's true for all values of theta. That's the important part of the identity, is that it's true for all values. So here's a trig identity. Tangent of theta is the same as sine of theta divided by the cosine of theta. Now, what I'm going to show you is not an official proof of that, but we will come back in and give some evidence to help you understand that. And since cotangent's the reciprocal of tangent, it stands to reason that cotangent would be cosine over sine. So there's another trig identity. Here's another one we're going to look at, that sine squared plus cosine squared is equal to 1. Now let's do a couple of verifications. By our definition, sine was opposite over hypotenuse, or it was y over r. Cosine was adjacent over hypotenuse, but to get you familiar with the other letters as well, let's put x over r. And if I'm simplifying and I have two fractions and I'm dividing them, we'll take the fraction in the numerator times the reciprocal of the fraction in the denominator. And in this case, the r's will cross reduce out. We're left with y over x. And y over x is the same definition of tangent, which is the same thing as the opposite over the adjacent. So we get the tangent. Cotangent, we're going to follow the similar route. Cosine is x over r. Sine is y over r. We've established that already. And instead of dividing two fractions, since we can't divide, let's take the fraction in the denominator and multiply by its reciprocal. Once again, the r's will cross reduce. So we're left with x over y. And x over y was our other definition for the cotangents. Well, let's look at the Pythagorean theorem here for sine squared plus cosine squared equals 1. We have in our right triangle r, the hypotenuse squared, is equal to the other two sides of the triangle, the x component side squared, the y component side squared. And what we're going to do is to substitute in our definitions. So sine was the y over the radius. It's also the opposite of the hypotenuse. But we're going to use the y value over the radius here, and then square it. Cosine squared, well, cosine is x over r, and then we're going to square that, and then we're going to leave the 1 alone. So squaring, that's y squared over r squared, x squared over r squared. There's a common denominator of r squared on this one. So we keep that common denominator to add the numerators. And x squared plus y squared is what goes in the numerator, and we keep the denominator r squared. Now remember that r squared is the same as x squared plus y squared. So if we do a little substitution, take this x squared plus y squared, replace it with r squared. We of course remember that anything divided by itself is equal to 1. And 1 of course does equal 1. It's not an official proof, but it's a verification that sine squared of theta plus cosine squared of theta is equal to 1. We're going to use some of those trig identities to help us solve example 2. To find the cosine of theta and tangent of theta if theta is an acute angle and the sine of theta is 1/3. So let's start out with our identity sine squared plus cosine squared equals 1. Sine, we've been told, is 1/3. So we're going to replace sine with 1/3 and we're going to square that. And we don't know anything about cosine yet, but we want to solve for it. So I'm going to subtract 1/3 quantity squared from both sides so I can get cosine squared of theta by itself. Once we do that, of course, 1/3 quantity squared is 1/9. 1 minus 1/9 is 8/9. But they didn't want us to find cosine squared, they want us to find cosine. So we need to take the square root of both sides. The square root of cosine squared is cosine. The square root of 8 in the numerator, that's the square root of 4 times the square root of 2, or 2 radical 2. In the denominator, the square root of 9 is 3. So we've just found the cosine. Let's use one of our other trig identities now to find the tangent. Tangent is sine divided by cosine. So tangent of theta is sine theta divided by cosine theta. We were told the sine of theta. We calculated the cosine of theta, and that's why we chose this identity. So let's substitute 1/3 in for the sine of theta. 2 square roots of 2 over 3 for the cosine of theta. And instead of dividing two fractions, we will multiply by the reciprocal. We'll notice that the 3's will cross-reduce, leaving me with 1 over 2 square roots of 2. But of course, we need to multiply numerator and denominator by the square root of 2 to get our answer in simplest radical form. So in the numerator, that's the square root of 2. And the denominator, the square root of 2 times the square root of 2 is the square root of 4, which is 2, times this 2, which gives me my answer. The tangent of theta is the square root of 2 over 4. All right, we got a potpourri here of several different identities and definitions. Let me remind you that first of all, from geometry, complementary angles are two angles whose sum is 90 degrees. No complementary angles are not angles that are free. And no complementary angles aren't when one angle looks at the other and says, you're acute angle. Well, yes, that's a nice compliment. But what we have is complementary angles, their sum is 90. That's important to remember because you may have noticed something about the names of these. Sine and cosine, tangent and cotangent, secant and cosecant. The prefix co here comes from the word complementary angles. So the cosine is the sine of its complement. Cotangent means the tangent of its complementary angle, and the cosecant will give you the secant of the complementary angle. And we call these co-functions. And the prefix here again, co, is coming from complementary angles. So here are some co-function identities. The sine of theta is equivalent to the cosine of 90 degrees minus theta. So for instance, the sine of 30 degrees would be the same as the cosine of 90 minus 30, which is the cosine of 60. They are co-functions of complementary angles 30 and 60 that I just mentioned. Here, if we turn that around, the cosine of theta is the same as the sine of 90 minus theta, again because cosine and sine are co-functions of complementary angles, their values would be the same. If we looked up the cosine of 1 degree, that would be the same as the sine of 90 minus 1 or the sine of 89 degrees. And likewise, that comes down through the rest of the co-functions. Tangent of theta is the same as the cotangent of 90 minus theta. So the tangent of 2 degrees is the same as the cotangent of 90 minus 2, or 88 degrees. Likewise, we turn that one around. Cotangent of theta is equivalent to the tangent of 90 minus theta. So cotangent of 3 degrees would be the same as the tangent of 90 minus 3, or 87 degrees. And secant and cosecant are co-functions. So the secant of angle theta is the same as the cosecant of its complement, 90 minus theta. If we chose 10 degrees for theta, secant of 10 degrees would be the same as the cosecant of 90 minus 10, which is the cosecant of 80 degrees. Turn that one around, cosecant of theta then is the same as the secant of 90 minus theta. So if we took the cosecant of 20 degrees, that's the same as the secant of 90 minus 20, or the same as the secant of 70 degrees. Alright, so those are the co-functions that are going to be important as we continue our progress in trigonometry. But before we go too much further, I want to take you a little tour of geometry. And there's two special right triangles you should remember. There's the 45, 45, 90 right triangle. And back then we might have said that this side was x, this side was x, and this side was x times the square root of 2. But when reduced to their lowest ratio, this side is 1, this side is 1, this side is the square root of 2. Remember from geometry that since these two angles are congruent, the sides opposite them would be congruent as well. So in a 45, 45, 90, if that side's 1, this side has to be 1. Do the Pythagorean theorem, the hypotenuse has to be the square root of 2. We also from geometry had another special right triangle, the 30, 60, 90 right triangle. And the shortest side, 1, is opposite the shortest angle. The longest side, 2, is opposite the largest angle, which is 90 degrees. And then the medium side, the square root of 3, is opposite the medium-sized angle, 60. Square root of 3 being approximately 1.732. That's in between 1 and 2. So we need to remember those ratios from geometry, and we're going to put them to work. How we're going to put them to work is we're going to fill in this little chart. This is a chart that you should very much be familiar with. And if you plan on going to pre-calculus, more than just being able to sit down and figure it out, you should probably have these familiar and common values memorized. So let's fill in the chart for the sine of 30. I'm going to stand at 30's point of view. Sine is opposite over hypotenuse, so the sine of 30 is 1/2. Cosine of 30, I'm going to stand at 30's point of view. Cosine is adjacent over hypotenuse, so that's the square root of 3 over 2. Tangent of 30, we're going to stand at 30's point of view. Tangent is opposite over adjacent, and 1 over the square root of 3 in simplest radical form is the square root of 3 over 3. Now don't forget these next three are reciprocals of sine, cosine, and tangent. So cosecant being the reciprocal of sine, so we're going to stand at the 30 point of view. Cosecant is hypotenuse over opposite. 2 over 1 is 2. Secant, we're going to stand at 30's point of view. Secant is hypotenuse over adjacent. 2 over the square root of 3 when put in simplest radical form is 2 square roots of 3 over 3, since we can't leave a radical in our denominator. Cotangent being the reciprocal of tangent, so standing at 30's point of view, cotangent is the old AO, adjacent over opposite, so that's the square root of 3 over 1. All right, let's continue this chart for 45 degrees, which means we're going to stand at this triangle. It doesn't matter which 45-degree angle you stand at, you're going to get the same results. So the sine is opposite over hypotenuse. 1 over the square root of 2 in simplest radical form is square root of 2 over 2. Cosine is adjacent over hypotenuse, and 1 over the square root of 2 is the square root of 2 over 2. Now, maybe you're noticing this, but I'll comment on this after we finish this chart. But if you remember your cofunctions, let's just take a quick look. Cofunctions are the same of complementary angles. 45 is a complementary angle with itself. 45 added to itself is 90. Sine and cosine are cofunctions, so they have the same values, square root of 2 over 2. Let's continue on with tangent. So from 45's point of view, tangent is opposite over adjacent. That's 1. Let's do cosecant. So from 45, cosecant is hypotenuse over opposite. That's the square root of 2 over 1. Secant is hypotenuse over adjacent, which is also the square root of 2 over 1. And again, since 45 is complementary with itself, secant and cosecant are cofunctions, so they're going to have the same values. Let's look at cotangent. Cotangent is adjacent over opposite, so 1 over 1 is 1. Tangent and cotangent are cofunctions, so they're going to have the same values. Now, I haven't mentioned that about 30 yet because the complement of 30 is 60 degrees. So let's fill in the chart for 60 degrees, and we will notice that the cofunctions of complementary angles are the same. So standing at 60's point of view, sine is opposite over hypotenuse. That's the square root of 3 over 2. Standing at 60's point of view, cosine is adjacent over hypotenuse, so that's 1 over 2. Standing at 60's point of view, the tangent is the opposite over the adjacent, so that's square root of 3 over 1. Standing at 60's point of view, cosecant is the hypotenuse over the opposite, so that's 2 over the square root of 3, which in simplest radical form is 2 square roots of 3 over 3. Secant, standing at 60's point of view, is hypotenuse over adjacent, so that's 2 over 1, which reduces to 2. And cotangent, standing at 60's point of view, is adjacent over opposite. 1 over the square root of 3 in simplest radical form is a square root of 3 over 3. Now let's look at those cofunctions of complementary angles. The sine of 30 should be the same as the cosine of 60. And because sine and cosine are cofunctions, and 30 and 60 are complementary angles, and yes, they're both 1/2. The cosine of 30 should be the same as the sine of 60, because sine and cosine are still cofunctions, and they're both square root of 3 over 2. Tangent of 30 should be the same as the cotangent of 60, and yes, they are both the square root of 3 over 3. Cosecant of 30 should be the same as the secant of 60, because that's cofunctions of complementary angles, that's the same. Secant of 30 should be the same as the cosecant of 60, which they are, because that's cofunctions of complementary angles. And then cotangent and tangent are cofunctions, so the cotangent of 30 should be the same as the tangent of 60. So we filled in this chart. These are values you should keep handy. You should definitely know these two triangles from geometry, be able to fill this chart in on your own, and better yet, if you're going on to pre-calculus, it would be really good if you had those memorized. Alright, so what we're going to do now is to put some of our trigonometry into practical use. We're not ready to break out the calculators yet. So we're going to use the following diagram to find the lengths of the missing sides. We've got a 30-degree angle. Our adjacent side is 12. Our opposite side is represented by A. Our hypotenuse is represented by C. Well, we know that the tangent of 30 is opposite over adjacent. So tangent of 30 would be A over 12. Now if we need the little chart as a refresher, you can look up the tangent of 30. And the tangent of 30 is the square root of 3 over 3. That equals A over 12. We have a proportion, so we multiply the product of the means equals the product of the extremes. And we get 3A is 12 square roots of 3. Divide both sides by 3, and A is 4 times the square root of 3. Alright, so that's finding one of our missing sides, A. Let's try to find our other missing side, C. Cosine of 30 is going to be adjacent, which is 12, over the hypotenuse, which is C. Let's refresh our memory and look up the cosine of 30 again. So here's 30. Cosine is the square root of 3 over 2. We're going to replace cosine of 30 with the square root of 3 over 2. Again, we have a proportion, so the product of the extremes equals the product of the means. So that gives me square root of 3 times C equals 2 times 12, which is 24. And let's continue to solve this by dividing both sides by the square root of 3. So C is 24 divided by the square root of 3. Don't forget we can't leave a radical in the denominator, so multiply numerator and denominator by the square root of 3. Reduce that, that's 24 square roots of 3 over 3. And that reduces to 24 over 3 reduces to 8 times the square root of 3. And without using any calculators, but just some common knowledge from geometry and remembering our trig ratios from Algebra 1, we're able to solve for the missing two sides of this triangle in example 3. Alright, let's do the same kind of thing, except now we are looking for an angle. So here's our diagram. We have triangle ABC. It's a right triangle. We know that this side is 3. We know that the hypotenuse is 6. So from A's point of view, we could say the cosine is the adjacent over the hypotenuse, which is 3 over 6. 3 over 6 reduces to a half. So let's look back in our chart in case we don't remember and see where the cosine is a half. So I looked down my list of cosine to see where it's a half. And sure enough, the cosine of 60 degrees is a half. So that means that angle A must be 60 degrees. And that's all they asked us to find in this one. If we had to find any of the other angles, that would not be difficult to do at all, because after all, in a triangle, all three angles add up to 180. This one's 90. Measure of angle A is 60. 90 and 60 we can add together to get 150. Subtract it from 180. Find out that angle B would be 30. So that's today's look in Chapter 12, Section 2 at trigonometry. We'll continue with more of this in our next lesson. Before then, you really want to have those 6 trig ratios memorized in terms of both opposite over hypotenuse, or in terms of also the y over r, x over r kind of notation. So please do that before next lesson.